Assalamualaikum and hi everyone. The topic for our class today is on capacitive transducer. Capacitive transducer is a device that changes measured variable into the change of capacitance value. So let's say we have a measured variable here, pressure. So any change in pressure value will causing the change in capacitance value. So let's say we have 1 bar pressure, and let's say the output of this capacitive transducer is around 1 farad. Then when the pressure change into 1.2 bar, then the capacitance value here will also change. So let's say it become 1.1 farad. So what we need to understand here is that when our measured variable change, it will cause the change in capacitance value. This is the basic concept for capacitive transducer. As for the design for capacitive transducer, it is very simple. A capacitive transducer only consists of 2 parallel plates, and in between that 2 parallel plates, it consists of dielectric material, or sometimes we call it insulating material. So basically, it looks like this. We have 2 plates, plate number 1, plate number 2. Then in between of this plate, we have insulating material, and this material can be air, can be water, can be specific chemical, and etc. Can be liquid, can be anything. Okay, so that is the basic design for capacitive transducer. This is the equation to calculate capacitance value. So capacitance will depend on 3 parameters, which is epsilon, A over D. Epsilon is a constant that represents the material in between the 2 plates. So basically, epsilon, we calculate epsilon using this equation, epsilon naught multiplied with epsilon r, where epsilon naught is a constant value for vacuum. Okay, it is 8.85 picofarad per meter, and it is constant. And in order to get epsilon, we have to multiply with epsilon r, where epsilon r is a relative dielectric constant for the material itself. So, for example here, if the material is vacuum or air, then the epsilon r value is 1. If the medium between the plate is a specific chemical, then it will have specific epsilon r value. So the total epsilon is epsilon naught multiplied with epsilon r. Okay, the second parameter that affect the capacitance value is distance, d. Okay, in this diagram it use x, but later we will use d a lot. So d or x is a distance between the plates in meter. So here is x. So it represents the distance between these 2 plates here. Okay. And the last variable is area. Area is the effective area of the plate. It also, we can understand the effective area as a shared area, meaning the area that both shared by the upper plate and bottom plate. For example here, this is the shared area for this condition. Okay, the both plate will have same area because it is parallel in this condition. But if the plate has moving to this side, then the shed area will be reduced because only, for example, we have two plates like this, and then it moved to this side. All right, so the shed area is only shed in this. Okay, so this is the only shed area that shed together between these two plates. Okay, so this is the shed area. Okay, so that is shed area. So the way to change area or to change the distance is by moving the plate, because we know that one plate is a fixed plate and another one is moving plate. So moving plate can be moved to the side, or it can also move up and down. If it is moved in up and down, meaning the distance here will change, right? The distance x will have to add some other value, or x minus some other value. Okay, that is when the plate moving up and down. If the moving plate move to the side, then the distance is the same, then only the shed area is changing. Okay, or we can also change the dielectric material between the two plates. So based on the equation to calculate the capacitance, there are three ways that we can use in order to design the transducer, which can cause the capacitance value to change. So the first one here is by variation of distance between two plates. So it means that we have fixed plate, then the moving plate will move up and down. So meaning the distance between the plate will change when the moving plate move to the up or the moving plate move to the down. The second way is by variation of shed area. Okay, so again we have fixed plate, then the plate is moving to this side. Okay, so at initially the shed area is at the maximum, but when the moving plate move a little bit to this side, then the shed area will reduce, so it will cause the changes in the capacitance value. And lastly, we have variation of dielectric constant. Okay, meaning here we have two fixed plate, both is fixed, but the material between these two plates is changing. Okay, so maybe at first it is only air, then suddenly it will consist of air plus something. Okay, so maybe half of that will become another liquid. Okay, so it's a combination of liquid plus air. So it means that the dielectric material that change between the plate. Okay, so meaning here the capacitance will change by fixing the epsilon, fixing the area, but change the distance. This is for the first methodology, the first way. Or what we can do is we can get the changes in capacitance value by fix this value, the dielectric material, and also the distance, but change the shed area. which is the second way by vary the shed area of plate. And last one is by change the dielectric constants in between the two plates. Okay, so A and D is constant. Okay, A constant, D constant. Only the epsilon here is changing. Therefore, the capacitance value will also change. This is the design for capacitive transducer using the first method. Okay, you can see here it is using the displacement changes. Alright, so initially the moving plate is at here. Okay, we have two plates with distance d, and the shed area is the same, and the dielectric material is the same. We can get a difference value in capacitor, meaning a change in capacitance value, by moving the plate up and down like this. So meaning A is still the same, dielectric is still the same, but distance now changing. So initially the distance is d, the new distance is d plus x. Okay, so you can see here the capacitance value for after x displacement is epsilon naught epsilon multiplied by A divided by d plus x. So the changes variable here is only the displacement. X is displacement. So different displacement of the moving plate will give you different value of capacitance value. So here we can use this kind of method to design a displacement sensor, like a push-pull displacement sensor, where based on the location of the probe, it will give you different displacement, then eventually give us different capacitance value. This is the second method in designing capacitive transducer by change the shed area. Okay, so for this diagram here, we have a fixed plate. Then the moving plate will move to the side. Okay, if the displacement is by x here, then the shed area will also reduce by width multiplied with x. Okay, W is width of the plate. Okay, W is the width of the plate. Okay, because we have width here, right? It should be the same for the fixed area. Okay, so you have, right, so this is the shed area, the new shed area, meaning the shed area now has been reduced when the plate has moving by some displacement of x. Okay, so meaning initially we have the capacitance value is C equal to epsilon naught epsilon R A over D, but now the new capacitance will have epsilon naught epsilon R over D, because this is constant, but now the area must minus area 2, where area 2 is considered to this side here. This is A2. Okay, so this is initially it is A, then minus with A2, where A2 can be calculated by width multiplied by x. This is width, this is x. So A2 is width multiplied by x. So putting the equation together, we have capacitance, epsilon naught epsilon r over d is constant because it's not changed. A is the initial area minus width multiplied by x. And width here is also fixed. Okay, this is also fixed, not meaning constant. Same value. The variable that change is only x here. Okay, x is our displacement when it moving to the side. Okay, x is the displacement. So again, this is another way to design a displacement sensor, but instead of move the plate up to the down, now we move the plate to the side. The third way to design a displacement sensor using capacitive transducer is by change the dielectric constants between the two plates. Meaning the plate here will have fixed distance and fixed area. So this is constant, not changing, fixed. All right. But the changes where the variable that change is only in terms of epsilon. Okay. So let's consider the diagram here. All right. So initial condition is that we only have epsilon 2 as our dielectric medium, meaning initially the plate is full of epsilon 2. But then it moved to the side, only the dielectric material moved to the side. Okay. And now it will have a combination of epsilon 1 plus epsilon 2. Okay, so meaning here epsilon 2 epsilon 2 is decreased by sum of x displacement, and the new epsilon, which is labeled here as epsilon 1, is around x value also. Okay, meaning we minus x of epsilon 2 but plus x of epsilon 1. Okay, so basically we said that, okay, the new equation is epsilon naught epsilon 1 a1 shed area 1 divided by d, and plus epsilon naught epsilon 2 area 2 plus by d. Even though I said a is constant, but the shed area is different for epsilon 1 and epsilon 2. But the total a1 plus a2 must equal to a. Okay, so a again is the shed area, meaning it is width multiplied by displacement, and a2 is width multiplied with L minus 1. L is the initial length of the plate here, L, but then it decreased by x because the dielectric material has displaced by x value. Okay, so that's why we have L minus x here. Okay, so putting back the value for A1 and A2 into the equation here, we get capacitance value is epsilon naught width over d, because this is constant, width constant, epsilon naught constant, distance is constant. All right, and again we can see that the change variable here is the displacement here, x. Okay, so it will affect the value of epsilon 2 and epsilon 1. You can see epsilon 2 and epsilon 1 here. Okay, but the value is the same. The change is only based on the displacement here. Is displacement. Okay, so this is the equation. that relates between displacement as our measured variable to the change of capacitance value. Okay, all the three ways that has been presented is relate between the displacement change to the capacitance value change. Okay, as a summary, a capacitive transducer is a transducer that converts from a measured variable to the change of capacitance value. So this is the basic design for capacitive transducer, where we have two plates separated by distance. In between that, we have a dielectric material. Okay, in order to design as a sensor, we can use by change the distance, change the shed area, or change the dielectric. Okay, so here we have few examples of using the principle of capacitive transducer, but not directly like the way that we discussed before. In the displacement sensor that we have discussed before, is directly use the method that we have said by change the distance, change the shed area, or change the dielectric constants. Okay, first one is here capacitive pressure sensor. Okay, if you look at this diagram here, what is the variable, meaning the method that used in here? Is it D, we change the D, or we change the area, or we change the dielectric? Which one do you think for this capacitive pressure sensor? Okay, so basically it is a distance. Okay, but the change of distance is not something that directly distance. We have to differentiate the distance here, meaning the distance is not the same all along the plate. Okay, where here we have maximum D at the end of both plate, but in between the distance we change based on the profile of the pressure applied to the diaphragm here. Normally this is diaphragm. How to diaphragm. I'm not sure how to write diaphragm. Okay, so this is diaphragm. It will expand when we apply pressure. Okay, so meaning the distance is not fixed along the plate, so we have to differentiate the value. Okay, the second one here is differential or push-pull displacement sensor. Okay, so for this type of sensor, it is basically use this method. Okay, change the distance, but the distance here can be plus some displacement or minus some displacement or plus some displacement. Okay, so because it only have it is push-pull displacement sensor. We have some like two condition of displacement. Okay, the third one here is a capacitive level sensor. Okay, so what do you think? Is it D, is it A, or is it epsilon? Okay, and where is our plate here? Right, so if you study this diagram, you can see that, okay, this is our plate. This is plate, but in rod form, and this is another plate. So this is plate number 1, the fixed one, and this is plate number 2, which is also fixed because it's not moving. Okay, and the distance is the same, so this is the distance T, distance between the two plates. And the shed area is calculated by, you need to open the rod, then you get the shed area, which is length here multiply with the circumference of the plate here, circumference of the circle here, okay, the circumference of this circle here, right? It's like circumference is 2 pi r, right? So that is the shed area. Now the change value is dielectric here, okay? So you may have combination of epsilon 1 or epsilon 1 plus epsilon 2 or just epsilon 2, okay? So based on the level. Let's say epsilon 1 is air, then when there is no any liquid in that tank, it only consists of epsilon 1. But when half of the tank has a liquid plus air, then it will be epsilon 1 plus epsilon 2. Or the tank full of the liquid, full with the liquid, then it only consists of epsilon 2. So the area will change based on the height of the liquid in that level. So that's how it becoming a level sensor. Okay, the last one here is capacitive humidity sensor. Okay, so for this one, I want you to think how this capacitive humidity sensor will work. Okay, think about how the displacement between the two plates changing, how about the shed area is changing, or is it the dielectric medium will change. Okay, so you need to think about that. I will ask in your assessment later. Lastly is on the signal conditioning for capacitive transducer. So we know that the output of capacitive transducer is in terms of capacitance value. So therefore, we need to convert capacitance value into a voltage. Okay, so we need to have a converter. So normally, for a converter, we will use AC Wheatstone bridge and together with differential amplifier. Okay, it is AC, right? Alternating current Wheatstone bridge. Okay, so it will have the same shape as DC Wheatstone bridge. Okay, only the power supply is in terms of AC. So we can see that the shape is the same as DC Wheatstone bridge. Okay, the difference is only at this power supply here. Okay, so this is AC power supply. The maximum amplitude is 10 volt and the frequency is 10 kilohertz. Okay, so initially we have all the capacitance having 888 picofarad. So we call this condition as null bridge, which will provide us 0 volt. And as you can see here, the Wheatstone bridge is able to convert any impedance. For a capacitor value, the impedance value is 1 over j omega c. But since all the term we have 1 over j omega, it will be cancelled out eventually. So that's why we only consider the capacitive value. Okay, so we have C1 over C1 plus C3 minus C2 over C2 plus C4. Okay, due to the concept of voltage divider. Alright, So let's example, initially we have at 880, but then CX here is our sensor, is our capacitive sensor. Okay, so now let's say the displacement has changed from 880 at the initial, it changed to 863. Okay, so due to that, we can see that the voltage output is also changed. All right, and the second condition here, the capacitance value is increasing for 800 from 880 to 898. Okay, then we still have a negative output here. Okay, and of course the signal conditioning, meaning the DC wisdom bridge, will be used together with differential amplifier. The function of differential amplifier is to calculate the difference value between point A and point B here. So in order to get this value, okay, we actually need to convert to the differential amplifier first, then only it will able to minus from VA minus VB. Alright, so that's all for the capacitive transducer. We have seen how to design a capacitive transducer, how to calculate the capacitance value, and then how to design as a displacement sensor and pressure sensor, level sensor, and etc. Okay. Next, we discuss on example on how to calculate the capacitance value based on different design. Okay, so for now, that's all. Thank you.